Hello, my name is FahadMian. Welcome to part one of my Breaking Logic series of videos, which is intended to demonstrate methods and ideas I've developed through informal learning and experience. If you haven't already seen my series introduction video that describes the purpose of the series, I'd recommend you do so. A link will be in the description. In this video, I'll create a physical model of conventional logic and show you how to break it and describe how and why it can be broken. In part two, I'll use this model as an analog that we can manipulate to help us guide our cognition through the problem-solving process. Logic, at its very core foundational level, would have come about when someone saw something over there and wanted to find out what it was, how it worked, and just generally to know more about it. So then that person goes and measures that thing or runs a test on it or does something with it. That foundation of logic and rules that we've built up on math and science, basic science and arithmetic and geometry, is essentially a reference for that thing that we saw over there that we were trying to make sense of. It's not actually that thing. It's not actually a real representation of that thing. It's just a constructed representation. By the time that we've actually measured and observed and tried to know more about that thing, it's changed. It's moved on. It's not the way it was, as it was, even through our own observation and senses. For example, with the optics on our eyes, we see the world completely upside down, and our visual cortex in the brain flips everything the right way around. It also manipulates perspective and depth and tone and things like that to attempt to correct things for us. But that's not really how things are in the world, in the real world. Now, when I was in primary school, I'm going to grab a piece of A4 paper here. It doesn't have to be A4, but roughly A4. And I'm going to cut a strip in it. And I'm going to remember that when I was in primary school and of early education and very susceptible to new ideas age, we were taught about basic geometry. And we were taught that one-dimensional is just something linear. So it's just a line. It just has one edge to it. And then we were taught that two-dimensional is something that has one edge in one direction and another edge in another direction. And it has only one side to it, or one plane. And then we were taught that three-dimensional things had, they existed in three different planes. So we've got there, and well, you know what I mean, three-dimensional. So those kind of ideas, when we're taught those ideas in primary school, they settle in our minds and they inform other things in life, complex things, decision-making, problem-solving techniques, things like that. So it's not just geometry. This is just a really, really simple, basic example of it. So this is just regular three-dimensional geometry. It's a tube or a cylinder, however you want to call it, tube, I guess. Now, what we're going to do to it, and this is something that you can show elementary school aged kids or primary school aged kids, anyone who understands basic geometry as I've described it, one-dimensional, two-dimensional, three-dimensional. And this is a fun little exercise. So what we're going to do, instead of connecting the two ends that way, we're going to twist and using one twist, and then connect this together. So now some of you will recognize this as a Mobius strip, which is some sort of specialized geometric shape. But for younger children who were taught about one-dimensional being single-edged and two-dimensional being one-sided and three-dimensional existing in three-dimensional space or three axes space, this would kind of break that convention, because it only has, if you follow your finger all around it, if you get the kids to follow their finger all around it and tell you how many edges are on this. They can get a pen if you want, sticky tape the ends together if you want, get them to draw a line along one edge, or however many edges they can find, and they'll find that there's only one edge on this thing. Then get them to draw a line on how many sides this has, how many planes or flat sides it has. And once they draw all the way around it, they find out that it only has one. So how does it exist in three-dimensional space? Well, science and geometry answers that, gives us another explanation for this, another definition, without really looking into what's actually going on here. But essentially, it's one-dimensional, two-dimensional, and three-dimensional by the explanations that are generally given to primary school and elementary school aged children through the education system. And what we're going to do, though, is look at it in a completely different way. So we've broken conventional logic with this, primary school, elementary school aged child logic with this. And the way it works is that normally when we have logic, we have either correct or incorrect, or we have on or off, or we have yes or no, or we have right or wrong, or we have A or B, or whatever the parameters or whatever the elements of the logical argument is. It's either one or the other. They're separated. That's separated logic, I'll call it that. I'm not sure if it's an actual term, but I'll call it separated logic, because generally we don't think about these things being together as a possibility. However, what we're doing with this, what we're going to do is assign elements of logic to this physical structure, and then we're going to manipulate it, and we're going to see how we go. So what I'm going to do is, and you can put on whatever label you want. I'm just going to put on, let's just do true with a T, and F for false on the other end. Now, this is going to lead into the second video here, but normally we don't, normally these are separated as these were separated. Normally they're separated, but now we've got a physical model where we can force these things to be together, where you have true and false together. And now anyone will tell you, likely tell you, that's crazy, man, that doesn't work. What are you talking about? Like explain yourself. So this what we're seeing here, true or false, the logic of true or false, is based on the system of logic from the rules and principles of science and general understanding that have been built up in our heads over the years that we think can't be broken. so we avoid trying to break them in any particular situation, you know, in the real world. But the real world is always moving, and we can't quite grasp it. Like if you like, we're just finding out now from science, from very, very close observation, that everything is vibrating and everything is moving. So if we've measured something and we want to know, okay, that thing is 2 centimeters, then by the time we've measured it and moved on, is it still two centimeters? We don't know. We just know what it was when we measured it, not what it actually is. So this twist that we do in here, this is the key. The twist is the key to breaking logic into some form of realistic consideration. So that twist is essentially a small perspective change that we're going to make while observing rationale and reason. We're going to break logic, but we're going to shift slightly in our perspective so that we can consider the real world. So we're not bound to the hard, separated logic anymore. So what this technique does, it lets you visualize and play with unseparated logic as you see fit, as long as you're aware that you're doing it. Please don't confuse true and false and make decisions based on that confusion without really thinking about it. You have to think about it, and you have to remain rational and reasonable, and it has to make sense. However you twist this, has to end up making sense, so that you can solve a problem, not cause more problems. You really want to make sure that you do this. And it isn't to suggest that true is always false, but just to use a little bit of your critical thinking skills and outside the box kind of skills, or delete the box completely if you want. But that shift in perspective, we're just doing it on paper. We're not making real world decisions with this right now, until we can really start to let it absorb into us the answers that we might get from doing something like this. Another interesting application, you can essentially put whatever labels on here that you want. Two things that people normally think are separated and form the basis of our logical argumentation in everyday life. It could be, beginning and end, zero and infinity, or a really heavy duty one might be life and death, or birth and death if you want. That's if you really want to get into the philosophical, spiritual end of it. But that's essentially it for our physical model of broken logic, and that is essentially how quantum logic works as well. So quantum logic makes various statements about how normal logic need not necessarily apply, and something can be on and off at the same time, or something can exist and not exist at the same time. The famous one being the thought experiment called Schrodinger's cat, where they put, it's just theoretical, but they said, if we put a cat in a box and we can't see the cat anymore, is the cat dead or alive? And the thought experiment, the conclusion, or the inquiry from that thought experiment essentially tells us that until we've opened and observed what's inside the box, the cat in the box is both dead and alive at the same time. So that's the kind of premise that we're going into. if you want to approach it from the level of science, but we're not approaching it from the level of science. This is from the process of unseparated logic. So I hope you'll join me for the next video where we'll use this paper model to prove that science is a belief system. Thanks for listening and watching.